Hi everyone, this is Mr. Zarzak, and in this screencast, I'm going to take you through how we measure and calculate power dissipated in a circuit. Let's get right to it. Okay, so as you probably remember, power is the rate of work divided by time. The deal is that with circuits, really all we can measure is the current and the voltage, okay? And so in order to measure the power dissipated, say, by this 30 ohm resistor in this circuit, we're going to have to be a little bit clever about it. All right, so first things first, we're going to write out work as the product of force times displacement. Okay, the reason I'm doing that is because that allows me to expand out the idea of power as work divided by time like this. I'm going to replace work in the power equation with force times displacement divided by time. Okay, and so I'm going to have to take several other steps in order to write power in terms of voltage and current. That's the idea. Okay, the intermediary steps I won't ask you to derive either in class or on a test, but it's useful to know where all this stuff comes from. Okay, so let's just keep going with this. Okay, if you remember from a while back, all right, we described the electric force experienced by some charge within a uniform electric field as just the product of the charge times the magnitude of the electric field. And so what I mean by that is I can write force is equal to Q times E. The analog there is to F is equal to ma, except I'm talking about charge and a uniform electric field. The way I get a uniform electric field is I connect a conductor to the terminals of a battery, and I set up a uniform electric field throughout the conductor and throughout whatever the conductors are connected to, aka the resistor in the circuit. Okay, so the deal is that when I do work against the electric field, that work must be done where a force is applied against the direction of an electric field. And what I mean by that is if we lift something in a gravity field, I'd apply a force upwards where the force of gravity acts downwards, and by applying that force upwards, I get a change in gravitational potential energy. Okay, so all I'm getting at is that we've used this trick before to derive equations where the force that we need to apply is just going to be in the opposite direction of the electric field times the charge. Don't get too hung up on that negative. You're going to see that it factors out here in just a second. All right, going back over to the other side here. Okay, I'm going to take and I'm going to replace force in the equation with what I just wrote. Okay, so I'm going to substitute in power is equal to, and then instead of force, I'm going to write negative EQ, close out my parentheses, okay, and then I cannot forget, I should say, the D divided by T. So I'm just rewriting power's work over time, okay, in terms of some other things. Okay, so if I just keep going with this, okay, you might also remember from our discussion of electric potential, all right, that if I have, say, parallel plates set up to generate a uniform electric field, well, then the voltage changes as a function of the distance of separation between the plates, all right, times the value of the electric field. Okay, and so what I'm getting at here is that in class we saw that the voltage goes up as the electric field gets bigger and can be calculated by multiplying the value of the electric field times the distance of separation between the two, with the little caveat there that the direction that voltage goes up is in the opposite direction that the electric field points. Okay, so just doing a little bit of a rearranging here, I'm going to rewrite this in terms of electric field, okay, where I've got this written as voltage divided by distance, okay, with that little negative sign over there. And then I'm just going to move that little negative sign over to the other side. So I'm going to write negative E is equal to voltage divided by distance, okay? And why I care about that, okay, is, well, I now have something written in terms of a negative E here, and I've got the negative E here, so I'm just going to actually sub that right out, okay? So again, another substitution over here. So power is equal to, inside my parentheses, voltage divided by distance times charge, close out those parentheses, And then don't forget, I've also got this d divided by t. Okay, well, now some things wind up, even though they look really messy right now, they wind up simplifying in that I've got a d in the denominator and I've got a d in the numerator, so that factors right out. Okay, and if you look at what I'm left with here, I've got power is equal to, let me clean that up a little bit here, power is equal to voltage times charge divided by time. And why we care about that, okay, is because, well, if we look at charge divided by time, that right there, that's the definition of current. Current is just a measurement of the rate at which charge flows in a circuit. Current is Q divided by T. And so by that logic, if I sub in for QT as I, I'm left with what I really care about. Okay, and all of this just gets me to power is equal to voltage times current, which is fantastic because in an electrical circuit, the two things that I have the ability to measure with meters are voltage and current. Now, the steps that I had to take to get to power is equal to voltage times current were pretty complicated, but the application of the power equation in a circuit is much, much simpler. Okay, so all the work to get there is going to be worth it. Okay, so looking at this circuit, I got a 10-volt source, and then I got a 30-ohm resistor. Okay, so the first thing I could do would be to connect an ammeter and a voltmeter into the circuit and measure the voltage across the resistor and the current flowing through it. However, since the 30-ohm resistor is the only thing in the circuit, all 10 volts have to drop across the 30-ohm resistor. And because I still know that Ohm's law is V is equal to IR, that doesn't change. Okay, well then to get the current in the circuit, I can just take the voltage and divide by the resistance. I've got one voltage source, and I've got one resistor, okay, and so the current just is 10 volts divided by 30 ohms, all right, and so the current is equivalent to approximately 0.33 amps. Once I have that, well, then I can measure the power just by using that new equation, P is equal to V times I. So I'm going to go ahead and do that. P is equal to voltage times current. Power is equal to 10 volts times 0.33 amps. And so the math is really simple here. I get this power is equal to 3.3, and my units are volts times amps, a volt amp. Okay, and so I wind up having a different unit for power that is equivalent to the volt amp, where I wind up abbreviating it for historical reasons. Okay, and so you might remember this little memory trick of what is the unit of power, and it's not a question, it's the answer. The power is equal to 0.33 watts, because a watt is equivalent to a volt amp. All right, that gets abbreviated as a W, so 3.3 W is 3.3 watts, which is 3.3 volt amps. Just as a little bit of an aside here, okay, if I take the volt amp and I expand that out, so volt times amps. Okay, so if you remember from before, a volt is equivalent to a joule per coulomb, and an amp is equivalent to a coulomb per second. A volt amp is equal to a watt, and so we see that a watt is just equal to a joule per second, which, if I think back to my original definition of power as work divided by time, well, the units of work is the joule, and the unit of time is the second. So my units are equivalent. And so we can think of as a volt amp as a watt, or a watt as a joule per second, and I'm talking about the same thing. In terms of power equation, I have a few more tricks I can do here if I combine Ohm's law and the power equation. And so what I mean by that is Ohm's law is just V equals IR, okay, and this can also be written as I is V divided by R, so I've just rearranged it, okay? So if I start with P is equal to I times V, okay, if I sub in voltage is equal to IR, look what happens. I wind up with this. I get I, and then I'm going to sub in for voltage I times R, and I wind up with power can also be written as I squared R. So by only knowing the current and the resistance, I can also calculate the power used up in a circuit or in a part of a circuit like a resistor. Okay, so that's pretty useful. So I'm going to write that as power is equal to I squared times R. Okay, and one more. Okay, if again I start with this power is equal to current times voltage, okay, well then instead of subbing out for the voltage, I'm going to sub out for the current because I can also write Ohm's law as I is equal to V divided by R. So if I go through and I do this, look what happens. I'm going to take and I'm going to sub out the I as V over R, so that's I right there, times V. And so I wind up with V times V in the numerator, which is V squared, and R in the denominator, which is R, which leaves me, if I simplify this out, power is also equal to V squared over R. So I have really three different ways to calculate power depending upon what I know about a circuit: voltage, current, or resistance. And so here I've supplied you with a summary of all the different equations and rules that we've derived for circuits thus far. Up in the upper left here, I've got my rules for series circuits. Remember that in a series circuit, the total voltage provided by the supply is just the sum of the voltage drops across the different circuit components like resistors or light bulbs. In a series circuit, the current is constant throughout. And to find the total resistance, I just add up the individual resistors. Whereas with a parallel circuit, okay, the rules are somewhat flipped. The voltage drops across any components in parallel are equal to the total voltage. In other words, all these voltage drops in a parallel branch are equivalent. The total current will break up into the parts of the parallel branch, so the individual pieces of the current add up to the total current. And I find the total resistance by using this little 1 over formula, where 1 over RT is equal to 1 over R1 plus 1 over R2 plus however many resistors I happen to have in parallel. All right, we just worked out the power equation, so P is equal to IV, P equals I squared over R, and P equals V squared over R. And the way I got these extra two in red here was just doing some substitution with Ohm's law and P is equal to IV. And then just so we don't forget, we've also got the resistor equation where R is resistance, rho here is resistivity, L is the length, and A is the cross-sectional area of the resistor that we build. This resistivity, okay, can be will change with temperature. So this is the reference resistance. This is the resistance at 20 degrees Celsius. And then this is the temperature coefficient. So this rho naught and this alpha, okay, are found in the table in your book. And this delta T is the difference in temperature from 20 degrees Celsius. And if you remember, we have a little shortcut version of this where if I happen to know the resistance at 20 degrees Celsius, because it's written on, say, the side of the resistor, I can look at how the resistance just varies with temperature. And this little approximately equal sign here is an equal sign that works for the operating temperature of the resistor. Okay, so as long as I don't put my resistor into a spot where it overheats or I freeze it, okay, as long as it's within its temperature of normal operation, these equations hold true. And for our purposes, we're not going to fry out any resistors. Okay. So there you have it. You now have all the rules and equations that we need to analyze simple series and simple parallel circuits. And these same rules can be applied in clever ways to make more complicated circuits, which we'll be covering in class shortly. This is Mr. Zarzik saying thanks for watching, and I'll see you in class.